The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're turning our attention to Pluto, what we used to think of as our ninth planet, and also to the mysterious new planet that might be orbiting on the outskirts of our solar system. Hello and welcome to Science for the People. I'm Rochelle Saunders. With me is Jeffery Moore, a research scientist at the NASA Ames Research Center and the Geology and Geophysics Imaging Team Leader for the New Horizons mission. His research is focused on a range of topics relating to evolution of planetary landscapes and crustal materials. Jeff, welcome to Science for the People.
Well, thank you.
Just for anybody who's living under a rock but still happens to be listening to this show, can you tell us very briefly what the New Horizons mission is?
The New Horizons mission is a flyby mission which was launched in 2006, which flew past the planet Pluto last July, taking lots of data, lots of images, lots of other types of data, and is now on its way to another much smaller Kuiper Belt object, which it should arrive at New Year's Day of 2019.
So New Horizons has collected a ton of data, but as a geologist, what is the most interesting data for you? I'm thinking if someone hands you the packet that includes all of the raw data, what do you flip to first?
Well, I, of course, flip to the images because the images that have resolutions with image scales of a kilometer per pixel or better are the ones which I can look at and begin to interpret the landscapes and try to understand what formed those landscapes and the order in which different features in the landscape performed. I usually go for a slightly more derived product. We made the big effort to take a lot of stereo coverage, and we can take the stereo images then to generate topographic maps so we can see what's up and what's down and how steep slopes are and how high or low things are. And we then use the topographic information as usually the most diagnostic tool for trying to understand landscape evolution.
This is actually something I was wondering is how do you look at a picture and figure out how high or deep or low a piece of landscape is on a planet so far away? Well,
that used to be difficult if you really took a single set of images and the images didn't have anything about them that helped you figure out how high or low things are. Now, of course, images are taken near the terminator, have shadows, and you can make shadow measurements and come up with height using that mechanism. And people have traditionally used that. In fact, for hundreds of years is how people determined the depths of craters on the moon back in the 17th, 18th, and 19th centuries. But with stereo imaging, it works just the very same way that the geological surveys of the United States and Canada fly aircraft and now spacecraft over the surfaces of their territories and take images in stereo, where you take pictures that look ahead of you, then take pictures of the same area that you've flown past to look back behind you, and you simply apply trigonometry to determine and parallax, the same principle that your stereo vision works in determining what's near you and what's far from you, to determine what's up and what's down, how much up, how much down it is, and what sort of slopes it has. And Pluto, as we anticipated, has a lot of bright and dark features on it already, and so trying to sort out what might have been shape from shading from what's simply something intrinsically bright and intrinsically dark, we thought would be a scary proposition. So we, as I said, intentionally went after high-quality stereo to sort out the landscape.
So let's talk about Pluto specifically. I've heard that scientists are surprised to find Pluto is a geologically active world. So first, what does that mean, geologically active? And second, why are we surprised about this?
Geological activity means that the landscape has new surfaces that we can see in the present time, that something is operating on Pluto or anywhere that makes a new surface. Like, for instance, on the Earth, when there's a volcanic eruption and some areas covered over with a lava flow, or there's a big landslide that covers over a pre-existing landscape, and you see that that's a fresh surface, and you can say, oh, that planet's geologically active because something is taking place which creates new surface area. In the case of Pluto or any planet, we first recognize fresh surfaces by the absence of craters on them, because since there is the incessant but slow rain of things crashing into planets, meteorites and so on, crashing into planets, that the longer a surface sits out exposed to space, the more craters will form on it. And if you see a surface such as we have seen on Pluto in the case of the informally named Sputnik Planum, that has no craters on it, we know that Sputnik Planum has basically a very young crater retention age. And we've determined that crater retention age to be not more than around 10 million years old, but of course it could have formed last week for all we know. It's so young we can't place any old date on it. So by geological standards, we consider that a fresh surface and that the planet is currently active.
So we can put a lower bound on that possible date, how old it could possibly be, and cut that off. But it literally could have been something that happened quite recently.
That's exactly right.
It's easy for us to say 10 million years, but I guess I don't really even know what that means from the standpoint of an Earth timescale or a meaningful timescale. So how would we put that in context?
Okay, so with 10 million years is not the lower bound, that's the upper bound. It can't be older than 10 million years old. It can be much younger.
Right.
Put that in context, well, the solar system, the Earth, Pluto, is about 4.5 billion years old. So something that's only 10 million years old is much less than 1% the total age of the solar system, or less than 1% the total age of Pluto. It seems like a long time to us because we mortal humans only live to be, if we're lucky, 70, 80, or 90 years old. And even evolution takes place at rates that 10 million years ago, our ancestors looked much more like apes than they look like what we look like today. So in some geologic time sense, 10 million years is a long time, but when you're dealing with planetary surfaces, which in many places in the solar system are billions of years old, and indeed there are billion-year-old surfaces on some locations on Pluto and almost everywhere on Pluto's large moon, Charon, when you can point to a region that's only less than 10 million years old, that's very young, geologically speaking.
So why are we so surprised to see that there's this really young geology on Pluto?
Well, Pluto is a small world. It's about the size of the Earth's moon, and many worlds of that size one doesn't think would have the energy sources to drive geological activity in the current epoch. Now, when you do see small worlds that have geological activity on them, like Saturn's moon Enceladus, that's because these moons are in a orbital resonance, a tidal situation where the tides being raised in the bodies by the interaction of the moon, in this case Enceladus, its sibling moons, and Saturn operate to basically heat up the interior through tidal friction, and you can get geological activity in a small world, but there was no obvious mechanism that we anticipated would operate to heat up Pluto. Pluto can only be heated by the radioactive minerals which are slowly decaying in its rocky interior. Now, I do want to mention that we think of Pluto as being an icy world, and indeed its surface is all made of different kinds of ices, but the interior has a large rocky core, and in fact, by mass, more of Pluto is rock than ice. And so this rocky component of the interior, the deep interior of Pluto, does have the usual radioactive minerals in it that, say, the Earth's crust does. And these radioactive minerals decay and produce modest heating. So there is modest heating being produced by the interior of Pluto. And the materials that are being mobilized by this modest heating, particularly the one that formed this big surface that seems to be very young, are very volatile materials. The surface of Sputnik Planum and the deposit which makes up Sputnik Planum is mostly, we think, frozen nitrogen ice. And frozen nitrogen ice is something which doesn't take a lot of heat to make it convect or flow. It's a very soft material. In fact, the analog material I use to describe the behavior of nitrogen ice is that it's a lot like silly putty on very short time scales. It's not really as soft as silly putty, but it, for instance, deforms more quickly than glacier ice does on the Earth.
Interesting. I love the silly putty analogy. Now this plane, it was Sputnik's plenum?
Sputnik plenum,
Is this the shape that most people would recognize as Pluto's heart?
Yes. Well, if you look at the heart, there's a right ventricle and a left ventricle, or if you want to think of it as, I rather think of it as the west ventricle. The west ventricle, which is the brighter, smoother surface, that is Sputnik plenum. And to put it in perspective, it's about the size of the state of Texas, and I wish I could tell you off the top of my head what the nearest Canadian province is similar to in size, but maybe something you'd out their province to state converter and come up with a proper province size.
I've looked at some closer shots and some zoomed in pictures on Pluto of the Sputnik plenum area, and there's definitely this kind of strange texture on the planes there. It's sort of bumpy, but it also has these kind of lines that look almost like you might expect potentially like as if there had been some drainage in certain areas. It's a really interesting texture to see on a planet like Pluto.
It has a lot of interesting textures. In the center of it, it has things which look like polygons or cells or whatever other descriptor you want to use. They're typically about 30 kilometers across, these cells. And the cells, in fact, are the evidence for convection. We think the cells are analogous to when you look down into a pot of gently warming oatmeal or porridge and see the rising and falling cells on the top of your porridge. Is exactly the same situation that's going on in the center of Sputnik plenum. That gentle heating from the interior of Pluto is causing this, as I said, relatively soft, plastically deforming. It deforms in time scales of years and decades to slowly rise in the center, spread out, and then descend along the peripheries of the individual cells. I mean, it's like looking down into a lava lamp, and lava lamps, in fact, are an example of a toy convection system.
So when we're looking at the heart shape that Pluto has on it, if you look at zoom-in pictures and kind of drill in really closely, you can see that there's quite a well-defined border between the kind of more jaggedy, mountainy region, and I'm not using it all appropriate geological terms here. Sorry, listeners. That's what Jeff is for. And it butts right up against the kind of plains. There's no kind of gentle change from one to the other. The definition of this line seems to be very abrupt. Is that normal? Is that something we would have expected to see? Well,
I can only speak for myself. I didn't expect to see a large soft deposit of nitrogen ice on Pluto, although I should have, but I didn't. But once I became aware of the mechanical properties of nitrogen ice at the appropriate temperature, the temperature is 40 degrees Kelvin, which is some ridiculous number like minus 390 degrees Fahrenheit, that it will, again, like silly putty, in the way silly putty will settle down inside the little plastic cup you're keeping it in, the nitrogen ice, which makes up the Sputnik plenum deposit, settles down into basically a geopotential surface where it's kind of more or less at some large-scale level, and it basically forms, for lack of a better term, sort of a shoreline with the much larger, much older topographic basin in which it sits. So it's not surprising that the boundary between the nitrogen ice deposit and its surroundings is sharp. And that boundary, if you look up what's going on up on the topographic rim beyond the deposit of nitrogen, changes a lot from place to place. In the northeastern portion of Sputnik plenum, or the Sputnik basin, which Sputnik plenum is found in, you can see that there are a lot of closely spaced valleys which are leading towards Sputnik plenum, which Canadians should recognize right away as being glacial valleys like you see along the coast of British Columbia. And in fact, that's what we think has gone on, is that in the past at least, maybe still happens in the future episodically, that solid nitrogen ice basically carves glacial valleys. That there have been and there still are nitrogen ice glaciers operating on Pluto.
So when you're looking at that kind of classic full shot of Pluto that's just gorgeous and I'm sure adorns many people's desktop computers, there's that kind of darker, more deeply red area or along the bottom, what I sort of think of as the bottom hemisphere of the planet. Is that just an artifacting in the image, or is it actually something that's less reflective down there?
Oh no, it's really much darker. So you're talking about a region we call Cthulhu Regio. That's again, it's an informal term. And it runs more or less along the equator of Pluto. If you want to look at your desktop picture of Pluto, and you see that big dark region that runs along the lower left 2/3 of the image, that pretty much marks out the equator. And that region is dark because it's covered by a material that's known as tholins. And what tholins are material which probably began as methane gas. And the methane gas, or methane ice for that matter, has been slowly radiated by either solar radiation or cosmic radiation and converted into heavier hydrocarbons. And as these heavier hydrocarbons themselves continue to be converted into even heavier hydrocarbons, they go from being white to yellow to red to brown to black. And so this region, Cthulhu Regio, is in fact really very dark. And in fact, many images we've had to play games of the contrast to keep Cthulhu Regio from being so dark you can't see what's going on inside of it.
I've also noticed that right along that sort of darker area, there's what looks to be a sort of crater with a little, I don't know, mountain or pimple in the middle of it. Mm-hmm. Is that just an artifact of the picture, or is that actually basically a mountain surrounded by some sort of moat?
No, that's exactly what it looks like. It's a large, relatively fresh crater, probably formed in the second half of solar system history, one might speculate. And what's going on there is that there's a smaller deposit of solid nitrogen setting down in the crater, and the crater itself has a central peak, as many craters do. You can look at the Earth's moon with a small telescope. You can see the fresh craters like Tycho, for instance, the crater that has the big ray system that everybody can see during a full moon, has a central peak in it. And so what has happened is that this relatively fresh central peak crater on Pluto has setting down on the floor between the crater rim and the central peak a deposit of nitrogen ice.
So I also want to talk a little bit about Pluto's moon Charon, because there's also some really interesting stuff going on here. When I look at a photo of the moon Charon, I'm quite surprised at how kind of grizzled and kind of beat up it looks when compared to Pluto, which it's orbiting. Is that something that we would expect to see, or is that surprising?
Oh, no, the fact that it's cratered is not surprising. In fact, I think, speaking for myself, I anticipated that Charon would turn out to be just a crater ball without a lot of other stuff going on it. But to our surprise, in fact, there's several interesting things going on Charon. First of all, the northern hemisphere and the southern hemisphere are relatively different from each other. The southern hemisphere has a much less cratered plains unit, which we've given the name Vulcan Planum after Mr. Spock's home planet. And the northern half of Charon is a much more cratered landscape that's been broken up by large tectonic rift systems. And we've given that region, the northern hemisphere, the name of Oz Terra, after the Oz stories of Dorothy et al. And then the very north pole of Charon is a dark patch called Mordor Macula, which we are still trying to understand what exactly made that patch. Something exotic, no doubt.
So it looks like Charon has a huge, I don't know, canyon system that goes kind of all the way across the planet. Is that basically what it is, a big canyon?
It certainly is. It's a big canyon system, we think, formed by extensional tectonics, and that's a fancy scientific word. It simply means that the interior of Charon has expanded sometime in its past, sometime in its early history, probably around 4 billion years ago. And this expansion of it basically caused the surface to break up into chunks, and as it was ruptured, much the same way that popcorn has, or some types of bread have an interesting, fracture pattern when the crust of the bread is broken up as the bread's interior expands. So something similar to that operated at Charon, we think around 4 billion years ago, maybe 500 million years after the formation of the solar system, to create the canyon systems that you see there breaking up the northern hemisphere of Charon.
What would cause a planet to expand like that? It's not something that I'm familiar with.
Well, the simplest explanation might even be the explanation is that Charon may have early in its history had a liquid water interior, and as the liquid water interior froze, the ice expanded and caused the interior to expand and the surface to crack.
So as someone who spent a lot of time looking at this data, what has surprised you the most?
Well, the one thing I didn't anticipate seeing were valleys and valley networks on Pluto. Prior to the encounter, we had a hard time imagining anything that was liquid that could run across the surface and carve valleys on Pluto the way that water and glaciers carve valleys on the Earth, and the way water carves valleys on Mars, and liquid methane carves valleys on Saturn's moon Titan. So that was one of the things that I guess I wasn't really prepared to see. So when we saw all these valley networks, we began to have to think about what could be making them. And as I've said earlier in the interview, we've now concluded they were most probably made by nitrogen glaciers. So that was a surprise. And then the one thing which has really surprised me, that I have a hard time understanding what I'm even looking at, is that there are two large topographic rises or mounds, like a better term, that are about 150 kilometers across and rise about 2 or 3 kilometers high, and then have big, deep depressions in their centers that are like 30 kilometers across and, 3 or 4 kilometers deep, which sure look a lot like volcanoes, although there hasn't ever been any big ice volcanic mountains seen elsewhere in the solar system. And moreover, since they are so tall, it means they can't be made out of nitrogen or even methane ice, because both those ices are just too soft to support kilometers worth of topography. So they probably have to be made out of water. So how water volcanoes were formed on Pluto, if that's indeed what they are, is indeed mysterious. And these putative volcanoes have either none or maybe 1 or 2 craters superposed on them. So they are probably young. They're probably like maybe 1 billion years old at oldest. So it's difficult to understand how they got there, and if they are even indeed really volcanoes or some other weird feature. They don't look erosional. They don't have erosional textures on their surface. They have constructional textures. So they have to be formed either by some kind of weird volcanism, ice volcanism we don't understand. We call that cryovolcanism, or else it's a combination of cryovolcanism and some form of tectonics. They have turned out to be truly amazing and puzzling. They're at least amongst the least expected things to see on Pluto, along with giant Texas-sized deposits of nitrogen ice and the valley networks.
It's really interesting how in a world with social media, missions like the New Horizons mission or a Curiosity rover on Mars end up getting this massive sort of public following, and in a lot of cases get somehow personified. I'm thinking of how the Curiosity rover tweets, and how the public emotion that was tied to the Rosetta mission, as well as the sort of memification and joy that people had as some of the initial images for the Pluto flyby were being released. It's just really great to be able to engage in this as part of the general public as it happens, because you do kind of really feel like you're a part of it, even though you don't get the data first, even though sometimes you have no idea what you're looking at. It really feels like we're kind of in it all together, which is cool.
Well, we are all in it together. I mean, the exploration of space is an endeavor that our entire species takes part in, and it's meant to be something that is enjoyed by and informs all of us, not just scientists, not just Americans, but everybody who has a sense of curiosity, which is an intrinsic property of our species. So I think we all do this because we think it's cool and it's fun, and it helps us understand how the world we live, or the universe we live in, works.
So just before we leave, the New Horizons mission is not finished yet. There is another object in your sights. Can you tell us a little bit about what you guys what you guys have pointed New Horizons at, and why you chose this object to have a closer look at?
Well, it was sort of chosen for us. The targets that we could fly to would have to be found within a relatively narrow cone of accessibility that extended beyond the New Horizons trajectory. So we have to burn some of our propellant to actually fly to one of these other targets. And so we first had to find such targets, and they were hard to find. We finally had to use the Hubble Space Telescope just the last several years to find anything that we could fly to. And fortunately, in 2014, we identified two objects we could potentially fly to one of those two objects. And after evaluating the feasibility of flying to one over the other, we picked one of them. We have spent our propellant to put ourselves on trajectory to go to one of these objects, and that's how it was selected. Both of them were maybe 30 to 50 kilometers across. They're much smaller than Pluto. They're more like the size of one of Pluto's small moons that we did take some pictures of. Now, this object, which currently is known as, I can't remember what I want to say it's MU or RU69 or something like that. It has a funny name. We're going to give it a real name. We just haven't given it a real name yet. We'll fly much closer to it than we flew even to Pluto. And so we'll get some very high resolution views of this object to see what did the surfaces of these, primordial Kuiper belt planetesimals look like. The reason they're interesting is that the Kuiper belt planetesimals, especially the ones in the region of space where we're traveling to, they're known as the so-called cold classical Kuiper belt objects, probably do represent, held in extreme cold storage, the basic building blocks of the solar system, including all the volatile stuff that went into forming the solar system. None of it has been presumably sublimated away or burned off or heated up and removed. And they set out in a region which may not have a lot of other things that ever come near it. So they may not even have a lot of craters on their surfaces. They may, look like what they looked like soon after they were accreted together at the dawn of solar system history, which is something, a texture, a landscape, which we've never seen before. So we're looking with great expectation for understanding both the composition of these small Kuiper belt objects and what their appearance can tell us about how they were put together, which in turn tells us how our entire solar system, including the world we live on, was initially put together. The pieces that went to put the Earth together, we're going to look at how those pieces were put together.
Well, thank you so much, sir. Thank you very much for your time and for telling me about, talking about Pluto. It's just such a fascinating mission, and some of the imagery and the surprises that we've had have just been really super cool.
I could agree more completely. It's been my pleasure.
If you'd like to learn more about Jeff Moore or the New Horizons mission to Pluto, we've got links to get you started in the episode notes on our website at scienceforthepeople.ca. After the break, we'll speak with Caltech professor and researcher Mike Brown about why we think there's another planet orbiting our sun, way out in the distant edge of our solar system. Stay tuned.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm Rochelle Saunders. With me is Dr. Mike Brown, professor of planetary astronomy at Caltech. He specializes in the discovery and study of bodies at the edges of our solar system. He's best known for his discovery of Eris, the most massive object found in the solar system in 150 years, and also notoriously as the guy who demoted Pluto from a real planet to a dwarf planet, which he explains in his book, How I Killed Pluto and Why It Had It Coming. He's here today not to talk about Pluto, but rather a possible different ninth planet that may already be part of our solar system. Mike, thanks for joining me.
Well, it's my pleasure.
So you helped take our solar system from 9 planets down to 8 and now potentially back up to 9 again. Is this a guilt thing, Mike? Are you trying to make it up to Pluto lovers out there?
It's funny, but it's really actually true that even a year before we started on this quest for Planet 9 or had an inkling that there was another planet out there, my daughter told me that this is what I needed to do. She said, people are going to still be mad at me forever about Pluto, and I just need to go find a new planet. And I laughed and thought that was a funny thing to say.
The name Planet 9 does seem a little bit cheeky.
I think it's the perfect name. It encapsulates an entire epoch in the history of the outer solar system, all in just one little name right there.
Okay, so let's maybe back up. So when did astronomers first start to think that there might be another planet out there?
I would say that the first time somebody thought that there might be another planet out there is about 1820. But that wasn't Planet 9. That was Planet 7. And in 1820 was when astronomers first realized that Uranus was moving not quite the way it should be, and used that movement to eventually, it took 26 years before they did it, but eventually predict the existence of Neptune. As soon as Neptune was found, that was 1846, and I think, the day after Neptune was found, astronomers started on the hunt for whatever was out past Neptune and looked at the perturbations by Neptune. So there's rarely been a time in the history of astronomy where some astronomer somewhere wasn't speculating that maybe there's another planet out there.
So there's quite a history of thinking that there might be another planet out in the edges.
And that history is, for the most part, wrong. So from 1846 until, I would say until now, all of the speculations about a planet past Neptune have been based on data that was later shown to be incorrect, or ideas that were potentially sort of dubious. And so it got to be this kind of, the Planet X, everybody has heard of Planet X. The search for Planet X and people looking for Planet X got to be this semi-crazy subset of astronomy where all you would have to say is that you were interested in Planet X, and all the other astronomers at the conference would slowly move away from your side of the room.
So what about this particular Planet X or Planet 9? When did the hunt for this one start?
So this one, it came when we were examining some of the data from objects in the outer solar system. This was about 2 years ago now. We were looking at some of the data, and there were some strange things going on. This is the way it always starts with planets in the outer solar system. You see something strange that you don't understand and immediately blame it on some unseen planet because you can't explain it. And we took the opposite approach. We, in this case, was me, and just 4 doors down is my colleague Konstantin Batygin. I noticed these patterns in where things were in the sky. I didn't have a very good explanation, so I walked down to his office, and I'm like, look at this. There's something weird happening there. Let's figure out what's going on. And we both agreed that the thing that was clearly not happening, and that we really wanted to disprove, first of all, was that it was a new planet, because we didn't want to be one of those crazy people talking about planets like they had for the last 150 years. So we were going to figure out what was happening and prove that there were no other planets out there to be found. And I guess we failed, because we tried very hard to show that something other than a planet could cause these objects, these distant objects in the Kuiper belt, they're all aligned in one direction, as if they've been pulled off in one direction. And there really is no explanation that we could come up with other than that there is a massive planet out there pulling these planets out of their normal orbits.
So when you say objects in the Kuiper belt, what are you actually talking about there? So
the Kuiper belt is, of course, this region out beyond Neptune. All the small bodies in this out beyond Neptune are part of this the Kuiper belt. Pluto is the largest one that we know of, but there are many, many, many others that are out there. And for the most part, they're on orbits. They're tilted. They're elongated. They don't go in nice, pretty circular orbits around the sun like the planets do. And some of them are on orbits that are so elongated that they go from where they are when we see them, which is sort of close to the orbital distance of Neptune, and they can go much, much further out. They can go on orbits that take something like 10 or 12,000 years to go around the sun. And the thing that we found that was so surprising is that these very distant objects, the ones that take the longest to go around the sun, the ones that travel the furthest away from the sun, these are the ones that, when they're going far away from the sun, they're always going off in one direction. They're not randomly going off around the sky like they should be. They have some preference. And that was the clue that there was something strange going on.
So they're all kind of spinning around the sun in kind of the same way?
they're all, if you drew their orbits, you would draw all the planetary orbits in circles, and you would have to draw them very small because we're going to draw really big things after that. Then you would take some of these very distant Kuiper Belt objects, and they would start close to the orbital distance of Neptune, but then you would draw an eccentric orbit that then takes it much, much further out before going back into Neptune again. And what's strange is that the ones that go that far, all of those orbits go in the same direction. You would basically draw them stacked on top of each other instead of like hands of a clock pointing in different directions, like hands of a clock all pointing in the same way.
So looking at those objects, I guess they're all going the same way, but for me, who's not an astronomer and not very good at astronomy, why is that weird?
So the strange thing about that is that over time, the position of objects in the solar system, their orientation, the direction that those orbits point, over time, they move. They precess. That's what it's called. They precess, and they make a full 360-degree precession around the sun in maybe 1 billion years. And they do it at a rate, every object in the outer solar system precesses at a different rate. So it's like having all of these objects be hands on a clock, and the clock, there are, six or eight hands on the clock, and all of them move at different speeds. And you walk in the room and you look up, and all of them are lined up. And either that means that you just got lucky and you happen to show up the one moment in history when all the hands line up, or something else is going on. In the case of the clock, you would say, probably somebody unplugged the clock and lined all the hands up and it doesn't work anymore. And in the case of the solar system, you say something is keeping all these objects pointing in the same direction. Something has broken the mechanism that usually keeps them spinning around.
So you said that you guys looked really hard for something that wasn't a planet, because originally you were trying to solve the mystery without kind of quote unquote resorting to a planet.
Yeah, we didn't want to be like sort of the crazy and / lazy approach, which is just to say, it must be a planet.
So what other things did you try to use to solve the problem that just didn't work?
The main one that we thought was going to work and thought made much more sense is it seemed plausible that if you had enough objects, enough mass in the outer solar system, and you started putting them out there, that they would end up making this configuration and keeping it together all by themselves. That there would be just sort of the gravitational pull of all the individual objects would be enough over time to keep them from spreading apart. And it seemed like a semi-elegant theory, and we could work out the math in certain ways. And it even almost kind of works if you squint really hard and turn your head sideways. But there was just no way to get enough mass out there in small bodies in the Kuiper Belt to keep this kind of ring in place the way we wanted it to. And we finally just had to give up, that this was just no way that could be the right answer. We tried a few other things that were even less successful, and in the end we had to break down and
try
a planet. That's true. Failures. We were failures.
Well, if that's a failure, then I'd say you're doing pretty good. So how does adding a planet into this mix kind of fix this problem, or solve the mystery, I guess is a better phrase.
So a planet is an amazing thing. If a planet on an eccentric orbit, so the interesting thing about Planet 9 is it's big, for one. It has to be about 10 times the mass of the Earth, and it has to be on a very elongated orbit. So the closest it ever comes is still something like 7 or 8 times the distance of Neptune, but the furthest is more like 30 times the distance of Neptune, and it takes something like 15,000 years to go around the sun. And if you put a planet on an orbit like that, the way orbits work is they spend a lot of time at their most distant, and then they come to their closest points where they travel very quickly, and they go back out again, and then they come quickly through their distant points, or through their close points. And it's only when it's close that it interacts very strongly with the rest of the solar system, and it does that just in these little moments. And it turns out that sort of interaction is exactly what you need to be able to keep these other little Kuiper Belt objects all lined up in that one direction. The Kuiper Belt objects are lined up in the opposite direction of the planet. Remember, the planet is very elongated. The Kuiper Belt objects are very elongated, but they point in opposite directions. And by doing that, they almost never spend any time close to each other. It's such a massive planet at 10 Earth masses. It would eject anything it ever got close to, but it's never gets close to these other objects because they spend so little time in those closest approaches.
Okay, so it kind of acts almost like a gravitational kind of counterweight, I guess?
You can sort of look at it that way, and it's a gravitational counterweight. It's a bully who gets rid of everybody else. So partially what happens is that if you started out the solar system with distant Kuiper Belt objects going off in all directions, Planet 9 would very quickly sweep by them and get rid of them. So it just throws them out of the solar system, and it just lets those ones that are in the opposite direction survive. So it's a counterweight, or it's those are the ones that hide best from it, or I'm not sure what your other favorite analogy would be, but those are the only ones that are allowed to stick around.
Okay, so we have a theory that we might be another planet out there. So how do you start thinking about its properties? I mean, how do you start to figure out its size and its orbit? Do you just kind of guess and plug it into a model to see if it works? Or is there a way you can start to determine these things based on the other data that you have?
So some of each. So the first thing we did is literally wrote down equations on the blackboard. This is Konstantin's specialty. He sat down and just wrote down how the solar system would behave with an eccentric planet. And with that, you can start to go through and look at what the important parts of the math, of the physics. And that's where we realized that it had to be an eccentric orbit, and it had to be something like 10 times the mass of the Earth. We realized there was just no way for a planet to have any effect on these Kuiper Belt objects unless those were the cases. So once we realized that's kind of a limited approach. It's nice to be able to write down the equations, but the only way you can write down equations is if you ignore a lot of what's going on and you really, really, really simplify. So we had a very simple model of what worked. And to really understand if it was going to work in the real solar system, we have to run detailed computer simulations. So the detailed computer simulations are, we basically create a solar system in the computer and impose Planet 9 on that solar system and start at the beginning of the solar system. We start with many, many, many objects in the Kuiper Belt. We watch what happens to them as they interact with Planet 9 and as they interact with all the other planets. And we did thousands and thousands and thousands of these computer simulations, and some of them work well to reproduce what we see in the sky, and some of them are complete failures, and some of them are somewhere in between. But by looking through all of those, we can finally start to hone in on what the properties are. We got very good at determining the average distance from the sun. If it's too close, it has too strong an effect and gets rid of other things. If it's too far away, it doesn't do very much. We could figure out the average distance. We could figure out how elongated the orbit is, because again, if it's very elongated, that means it'll sweep in close to the sun, cause too many problems. So we could constrain that. We could constrain the mass very well. If it's not massive enough, it doesn't do anything. If it's too massive, it destroys the solar system, and that's kind of considered bad. So, all these different ways we could slowly work to a pretty nice constraint on what we think it's like and what kind of orbit we think it has.
So is it kind of like trying to find the mins and maxes?
Yeah, it's sort of. It's not we don't have a perfect way of comparing the computer simulations to the real solar system because we have a limited number of objects, but it's more or less that same way. You're kind of exploring all the different parameters and figuring out how to optimize each of them until you figure out as much as you can.
So we have some idea that it's quite massive. I think you said 10 times Earth's Earth's mass. Is that correct?
Yes.
But what about some of its other properties? So we have some idea of its mass and we have some idea of its orbit. What about what it might be made of?
So our hypothesis, our theory for Planet 9 is totally agnostic about what it's made out of. All we can tell from what we see in the distant Kuiper Belt objects is how massive it is. We don't care if it's 10 times the mass of the Earth and it's made out of hamburgers or it's made out of diamonds or anything else. 10 times the mass of the Earth is 10 times the mass of the Earth. But we can speculate, and I think we can speculate pretty intelligently about what it probably is. And the reason is that 10 Earth masses is an interesting mass. It's between Earth, which is one Earth mass, and Uranus and Neptune are right about 15 Earth masses. And we don't have anything like that in the solar system. So at first you might think, what is it more like the Earth, or is it more like Neptune? Is it a giant Earth thing with a solid surface you could walk around on, or is it a gas giant like Neptune, just a little smaller? And normally we might have no way of knowing that, except that if you look around the galaxy at all the other stars in the galaxy where we've been finding planets over the past few years, we've realized that actually planets that are about 10 times the mass of the Earth are the most common type of planet in the entire in the entire galaxy. And so we know we've seen a ton of these 10 Earth mass planets, and they're almost always miniature Neptunes rather than giant Earths. So we can guess that here in the solar system, our 10 Earth mass planet is like all these other ones around the galaxy, and it's going to be a little miniature gas giant that's a lot like Uranus and Neptune.
So you mentioned earlier on in the interview that the additional planets, rogue planets as they were, had sort of been a bit of a reoccurring theme in astronomy circles for a while, and that people tended to sort of settle away from people who proposed planets. So when you guys said, hey, we think this might actually maybe for reals be out there, what was the response?
So we have to say we were a bit nervous because we knew the history of what happens when people say this. We worked really hard to make this as rock solid, airtight as possible, and then we sat back and waited to see. And the question we had for ourselves was, how long before the first paper appears saying, these guys are stupid. Here's why there's no such thing as Planet 9, or perhaps even no papers ever appear and we're just totally ignored. And it's strange that it's been the opposite. There have now been something like 30 papers in the past 6 months since we proposed Planet 9, talking about Planet 9, thinking about how you would find it, what it would be like, saying, yeah, we think it's there too, from other evidence. There have been 0 papers so far trying to refute the idea, which is surprising to me. I mean, astronomers love to do that sort of thing. A paper like ours gets a lot of attention and proposes something pretty bold. What could be more fun than showing that those guys who did it are crazy and don't know what they're talking about? That's as good as it gets in astronomy.
It strikes me as something that would be very difficult to do as an astronomer, because this seems like a really exciting thing, sort of in all caps, and to try and be both really excited about it, but also try and be your own worst critic to make sure that you're not being blinded by that excitement. That seems like a balance that might be really hard to find sometimes.
Oh, you're absolutely right. I mean, the hardest thing to do is the most important thing to do is just to not believe yourself very much. And the convenient thing, I think, one of the nice things is that with the pair of us, me and Constantine, with very complementary skills, and we just refused to let the other slide on anything. If there was something that just didn't quite make sense to me, I would just nag Constantine until I understood it, or it got fixed, or something in the same way if something didn't quite go. So he and I both, we learned a tremendous amount from each other this way. But I really think that was the biggest quality control on this, was just we both knew that it had to be right, or we couldn't publish it. We couldn't say, there's some evidence, it's not great, maybe there's a planet. That would be terrible. And if we were going to make the case that it's really out there, we had better be as close as possible to believing in ourselves as we could. And I would say, even though I say that the goal is to not believe yourself very much, it's hard these days for me to imagine that there are things happening in the solar system that we see. It's hard for me to imagine that there is another explanation. Maybe somebody will come up with an alternative explanation, but since nobody has, and I'm pretty convinced.
So if you were to step into the shoes of maybe the biggest critic of this, or the biggest skeptic, what would you say the chances are that there is a Planet 9 out there?
0.
Oh.
I'm sure that there are critics who would say that.
And what do you think?
Somewhere between 99 and 100.
So we really have a full spectrum here. That's great.
Well, you asked for the biggest critics. If the honest skeptics, it's interesting. So people tend to be more skeptical if they haven't actually read the papers, and they just think, like me. If I just had heard, somebody proposed that there's a planet out there, and I'd be like, another of those people. It's very easy to sort of just be dismissive without having read things. Now that's why it's gratifying that so many astronomers have written papers generally supporting the idea.
So what do other astronomers think of the current state of the Planet 9 hypothesis and search? I mean, is it generally accepted, or are there people who are sure it isn't there?
I think, as far as I can tell, for the most part, people are pretty convinced. And I would say, everyone is holding out to see it in real life. But I think people find the evidence pretty compelling and find it hard to come up with another explanation. There are always going to be skeptics who, kind of want to show that they're right and you're wrong. And I'm sure that those skeptics are in the middle of writing their papers right now, trying to refute the idea. But I haven't seen many yet. You hear people sort of say, well, it's not very good evidence, and I think that mostly those people have not looked at it themselves. So far, when people look at it themselves, they find it pretty convincing, I think.
Okay, so how do we go about trying to find this planet? We have some idea of its properties, and we sort of know what its behavior might be, but how do we actually find it?
So the one other thing we know its properties, its behavior, and we have a pretty good idea of its orbital plane. So it's tilted by a little bit compared to the planets in the solar system. It's tilted by about 20, 30 degrees, but we know about what that plane is. What that means in practice is that we know the swath of sky that it travels through. It doesn't go through the ecliptic, the zodiac. It doesn't go through those constellations. It's tilted from those constellations, so that's where all the planets are. But it goes through a very clear set, so we know where to look around the sky. Unfortunately, we don't know which constellation it's in right now. So it could be anywhere 360 degrees around the sky, but along that one path. So we can rule out a lot of the sky, but we still have a pretty big search to do. We've actually done a good job of ruling out some of that search region by going through old data. So this is my summer vacation project, is to go through every bit of old data that I can possibly get my hands on and see if there's any chance that Planet 9 was accidentally pictured before and people didn't notice it. And if we get lucky, we'll find it in that. I suspect the answer is we won't find it in that. And once we've ruled out about half the sky that we have old pictures of, I think that we will have to end up mounting a big survey of the other half of the swath of the sky.
So it does get pretty far away from where we are now, from the Earth. So is it actually bright enough for us to be able to see it with our current telescopes at all points in its orbit?
So the nice thing is it is just exactly bright enough for us to be able to see at its most distant point in its orbit. It's bright enough to see with the biggest telescopes on Earth. So you will need something like the Subaru telescope on Mauna Kea in Hawaii, or the Keck telescope on Mauna Kea. Those are the telescopes that will be needed if it's in its most distant location. But you don't need something bigger, and that's a great thing. If it had turned out to have been 2 times further away or a little bit smaller, there's a good chance that we would not be able to find it for decades until we get another generation of telescopes. But it is just exactly in the sweet spot for the telescopes we have now. So we will definitely be finding this thing pretty soon.
So we don't have any idea where in its potential orbital path it is right now?
We've ruled out some parts of it, but basically by its gravitational influence, we can't tell where it is. So the only way we can rule it out is by hoping that hoping that we should have seen it in other data.
So when you're looking through a telescope at the night sky and a planet's that far away, how do you tell a planet from a star? Asks the super astronomy noob.
So this part's super easy. Planets and everything else in the solar system move compared to the stars. So this is what we do all day long, all night long. We take pictures of the sky and we simply look at all of the stars and the galaxies and everything else that are in the same spot hour after hour, and then you find that one little thing that moves slightly across the sky, and that's part of our solar system. Planet 9 is going to be so far away that it will be the slowest moving thing we ever see, but it's still something that we can see its motion just from night to night.
So is there any other way we can narrow down the search? I heard somewhere that there might be a way to use the data from the Cassini probe to help narrow down the search a bit.
Yeah, so this is an interesting idea that there was one of the very first papers that came out after ours was using what Cassini does very well is tells you very precisely the distance from the Earth to Saturn. And so you can imagine that if there's a big planet out there, it slightly changes the distance from Earth to Saturn as Earth and Saturn go around the sun. And an analysis of that effect has been done and has potentially pointed to a location where Planet 9 might be. There are questions about the data that people who understand this much more than I do have, who think that it's not, that it doesn't work as well as it does. And I don't know. I've looked at the data. I've looked at the new data that the other people have, and I understand all the arguments on both sides. But it is an incredibly technical challenge, because it's not just that you have to understand, you look at the distance from the Earth to Saturn. The distance from Earth to Saturn is affected by everything in our solar system. And so you have to have the rest of your solar system perfect, or you can't predict the distance from Earth to Saturn. And you can't get everything in your solar system perfect if the entire time you were trying to figure out your solar system, there was a ninth planet that you didn't know anything about. And so the whole question is like whether or not it's very complicated. And every time we think maybe we should go and do this analysis ourselves, we spend half a day going through it and then just throw up our hands and realize that it's really hard. You basically have to go through the entire history of human astronomy and try to redo the solar system from scratch and include a Planet 9. That
does sound really, really difficult given how long it took us to get this far.
Yeah.
Definitely doesn't sound like something you can do in 5 minutes.
Yeah, so I think we've given up that one.
So, of course, and it was probably inevitable, but there are a number of headlines that suggest Planet 9 might be on some sort of eventual collision course with Earth, or that it might hurl comets toward us. Care to comment on these doom scenarios?
Yeah, so I just like to remind people that, Planet 9, the closest it ever gets to the Earth is 7 times the distance to Neptune, which is something like 40 times the distance to Jupiter. And Jupiter is something like 30 times more massive than Planet 9. So what I would say is, if you're worried about Planet 9 causing problems, you should be terrified of Jupiter. It's much closer and much badder. So it's worth being scared.
So all things considered, though, if we do have to go to our doom, I can think of worse ways than a Hollywood-esque epic collision of planets.
As I say, if there were going to be like a giant comet shower and things raining down from the sky, it would take a good 10-15 minutes before we all died, and it would be spectacular. So, don't go run into the caves. Go climb on the biggest mountain you can find and watch, because it'll be, the show of a lifetime, literally.
Mike, thank you so much for being here, and good luck with the search.
Thank you.
And if you want to learn more about Mike Brown, his work, how he killed Pluto, or the search for Planet 9, we've got some links to get you started in the show notes, which you can find at scienceforthepeople.ca.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten. Coordination and additional behind-the-scenes support comes from the enthusiastic Skepcheck Network team. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. Science for the People is listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount. In return, we regularly post special patron-only extra content and after-show casual conversations with guests. This show is created in partnership with the Skeptic Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skeptic at skeptic.org. The show is hosted by Rochelle Saunders and me, Desiree Schell.